Page 18 of exponentials. The weight, W subscript T, grams of radioactive substance remaining after T years is given by this equation. I put the equation into the screen y equals. Find the initial weight of the radioactive substance. Remember that the initial weight is always the multiplier here if the equation is just in the form of the initial amount times an exponential. So the initial amount is 1,000. Okay, let's find the weight after 10 years, 100 years, and 1,000 years. And the easiest way to do that is with a second table. So first we'll look at it after 10 years. So we're going to look for when x equals 10. When x equals 10, y equals 812. Okay, usually in IB we give 3 significant figures, so 812. Then it says to find after 100 years. Now you might have a certain amount of impatience scrolling down to 100, so one trick you can do is you can change the jump using the plus sign. You could say I'm going to jump by 10s instead of 1s. And then now I can easily go to 100. 100, the weight remaining is 125. Remember, we're talking about radioactive decay. Did you know that if you have radioactive waste, the only way for it to become less radioactive is to wait? So it reduces to a fraction of what the radioactive used to be after a period called the half-life. It reduces to half of what it used to be after a half-life. Half-lives are usually like 100-something years. So let's go to 1,000 years. So 1,000 years, now let's jump by 100. Now we're jumping by 100, and if you look, after 1,000 years, it's quite low. It's 9.3 times 10 to the negative 7th. Remember that this e here just means times 10 to the negative 7th. Okay, times 10 to the negative 7th. So now we're going to graph this quantity against t using the information from A and B. So first we're going to mark 1,000 here. Let's say that's 1,000. So the first point is 0, 1,000. The last point is going to be after 1,000 years. It's pretty much going to be 0, 2, 4, 6, 8, 10. So that's pretty much going to be 0. And after 100 years, it's going to be 125. So 100 years is here. 125 is going to be about here. Okay, so this graph is going to look kind of a very sharply dropping, right? Something like that. Okay. Then it says, use your graph or graphics calculator to find the time when 10 grams of substance remain. Okay, so since there's so many numbers here, I think the best way to do this is to do the way I taught you in the last video. So we're going to do a graph. And this graph, we're going to look for when it's 10 grams. I'm going to put like, I don't know. Let's see, it's going to be past 100, right? Because in 100 years, it was 125 grams. So maybe like, I'm going to put maybe 500 years. 500. And then we'll graph, and maybe we're going to have to do a, yeah. Let's adjust our zoom fit. To adjust our Y. Okay, that's a little better. And so now we're looking, when does it drop down to 10? So we're going to put a second equation in our y equals screen. We're going to put y equals 10. And then we're going to graph it. And then we're going to do a second calc intersect. And the first curve is the exponent function, yes. The second curve is y equals 10, yes. And then it doesn't really matter when we guess because there's only one intersection. So it says the intersection is going to be 221. Oops. 221 years, comma, 10. Okay? So that's how long it takes. 220 years to reduce down to 10 grams. Write an expression for the amount of substance that has decayed after t years. The amount of substance that has decayed. So like the amount that's here is the amount that's remaining, okay? So if we want the amount that has decayed, then we would probably want to take the original amount and subtract the amount remaining. That would give us the amount decayed. So it looks kind of like that, okay? So let's say we'll call it D, decayed. So if you want to, you could factor out the 1,000, but sometimes they're written in this format. Okay? All right, let's go down to number 5. Again, with radioactive decay. Okay, so we have a uranium-235 sample remaining after T years is given by the formula, and then it gives us this formula. Find the original weight. Okay, remember the original weight is always the multiplier here, so I'm going to put W0. And let's see. The percentage weight loss after 1,000 years. So you notice since they didn't actually give us an initial amount, they just gave us this constant here, they can't really ask us for specific numbers either, and we can't even use the calculator, it seems, okay? Let's see how we're going to figure this out. We're going to find the percentage weight loss after 1,000 years. Okay, so can I put this in the calculator without a number? Well, what if I just assume a number? Like, since we're looking at percentages, what if I assume that the initial quantity is like 100? And then the rest of it, I'll just put it in as is. So 2 to the power of negative 0.0002. Is that right? Okay, so now let's look at the table and see what happens after 1,000 years. I still have it set to an increment of 100, so it's easy to get to 1,000. So after 1,000, I'm going to have the quantity 87.055. I started with 100, and now I have 87.00055. So the weight loss is going to be, so it's 100% minus the remaining, which is 87.1%. So the loss is going to be 12.9%. Okay. Then it says, find the time required until 1/512 of the sample remains. So 1/512 is 0.00195. 0.00195. So what I'm looking for in my table is when does it equal, let's see, 0.00195 in percentage is equal to 0.195%. Still like almost nothing, right? So let's use the other method where we actually like draw another line in the graph. So we'll go to y equals and we'll draw a horizontal line at the line 0.195. I'm not going to do 0.00195 because 0.0095 is a fraction. I want a percent, the percent compared to 100% because I put in 100 as the initial value here. So I'm going to put a line here at 0.195. Okay, and then I graph. Okay, and then maybe I need to put in a huge value of 500, like maybe 10,000. Okay, there's my exponential function. and then my horizontal line is somewhere in there too. I can't really see it, right? Maybe I will do a zoom fit, and then I can see it better. One of the trickiest things about using the calculator is being good at using window and zoom. You really have to just do a lot of graphs and, find your own favorite ways of doing things. Don't take my word for it. There's a horizontal line here, but I don't think we can see it. Okay, so let's increase the window here. I need to make it go even lower. So instead of a 10,000, I'm going to say maybe it's 50,000. Now I'll graph again. Okay. All right, maybe now we're going to be able to find it. So let's see if we can find an intersection between the two graphs. I can't even see it, so enter, enter, enter. There it is, 45,012. Okay, so the time required to get to here is 45,012 years. Okay, all right, that takes quite a long time.